Okay, so we had yesterday just going over the basics for a graph data structure, and then I described the algorithm for breadth-first search. And we were looking at quite a simple graph. It only had 4 nodes. And you can see what we finished off with here on the last video. So you're thinking at the end there with the parents array, how we could throw that into the constructor and build up a tree where you've got all of the nodes from the original graph G, but with the tree T, you're only left with the edges such that there are no cycles, and you could travel from any node in the tree to any other node. So there exists a path between any pair of nodes in your graph. Okay, you could probably have snuck a peek at the code when we were looking at the source code file for graph.java. And I've got that method we're going to take a quick look at. And if you're curious about how to actually program it, this is what it looks like. The ideal is if you're doing your own studying and you hear me describe something like this yesterday, but you don't get to see the entire source code for it, then the description, what I would do is I'd sit down and I'd try to write out for myself what was the pseudocode that I described. And I tried to do that in my own words the best that I could. And I realized that I'm just giving a description with an example just to get you started thinking about what breadth first search is doing. But if you have pseudocode written in your own words, that's a way that you can start to move forward how you could think to program it yourself before being shown how to program it. And you might program a slightly different way, and that's okay, it would be good practice. Doing this gives you a chance to really pick apart what it is that you do in your own studying, and you could have that once you realize what it is that you're doing, you could take that and you actually apply it to your studying in other courses even. So being keen is actually really helpful. You can do quite well in your upper level courses. Is this the type of approach you would do, especially with your programming and you're looking at other computer science courses? If you tried to program this on your own first, which I realize is quite a tall ask in second year, now that we're getting near the end of the second year course, Comp 251, you want to start thinking this way, because then when you move on to your other upper level classes, you've got that advantage and you're good to go. So just looking at breadth first search itself, based off my description, we had a couple of arrays. So when you look at the first few lines of code, we've got I shouldn't be grabbing the size for my queue. And that's a bug that I noticed right away because I'm falling back on the other data structures thinking, oh, we always use size to describe the number of nodes. So this is actually a good mistake on my part to re-emphasize that the size is not keeping track of the number of nodes, it's keeping track of the number of edges. So what I would do instead is, I probably conflated those two things. So I'm going through the variable adjacency that has my linked lists in that collection. And then we have the variable size that would be keeping track of the number of edges. So it is worth my time in this video here just to re-emphasize the difference between these two things. And we come back down here, and so it's not the field that I'm grabbing that gives the number of edges. I'm getting the number of linked lists that I've got, and that corresponds to the number of nodes that I have in my graph. Okay, so don't be like me, and then when I first look at it, I conflate the concepts in my mind, then I have to remind myself. Might have to do that and reconsider this again later. So I belabor the point. But just make sure that you're keeping those two concepts straight. In graph theory, they use capital N to represent the number of nodes. Sometimes you might see in other people's code lowercase n, but I just like to use uppercase N just because math, they're usually using uppercase N. Once we know how many nodes there are in our data structure, we can set up the arrays, because the queue and then the number of nodes that we're visiting, we want to keep track of which ones we have visited in the queue. Because we're using this array to decide whether we should be placing nodes that we haven't visited yet onto the end of the queue. So this would be an array of Boolean, and of course we're making that decision per node. So again, the size of this array would be the number of nodes. I've already described in the previous video the parents array, and again, you should be familiar with this from the union find algorithms we looked at during the first week. And that's a long time ago, so I realize you might have to think back, okay, how did we use this? So if you're still struggling with that, I would say go back and rewatch the first video for this week and just think through how I'm describing the setup for the parents array. And again, every node for a tree, all you have to do is keep track of the one other node for its parent. So we're storing the labels for each node, and then from that we can pass it into the constructor for another graph. And then finally we can return another instance of graph that will be our tree. Now the fancy name for this kind of tree that we're getting from breadth first search, this is a spanning tree. So what that means is every node in the original input. So the graph that I'm working with, remember, this is not a static method. So we're calling it through some instance of graph. So it already has the adjacency lists set up for that particular graph. And I would consider that to be the input for our breadth first search. A finer point might be is that if you wanted to also query an empty graph and it doesn't have any nodes at all, and so it might not be associated with a particular instance, the instance itself might be null, then we would change the implementation for this method to be static, but then we would have to pass in a particular instance of graph as a parameter. So then we would have to do graph G, and I usually call some variable for our graph. I usually use capital letters like G or T or maybe H. And then we could run the algorithm even if the instance for the graph was just null. And in that case, I would be returning a tree that was null, and that would be a very trivial case to deal with. Okay, I don't have it set up like that, but you could change the implementation to be like this. All right, moving on. Once we have a queue set up, then we've got two indices. The first index would be for the front of the queue. That would be a lower number compared with the second index, keeping track of the back of the queue. So I'm always going to be adding new nodes that we're visiting to the end of the queue, and then I will process nodes at the front of the queue. So you'll get a better idea of what that means when we look at the loop right below. We want to get things set up, so we place our first node at the front of the queue. And so the back is currently the same as the front. They both have the same value. But as soon as we add this input node U, we add it to the queue. We're incrementing the index back to the next available slot in the array for the queue. And then the visited value for the node u, we will treat this as if it has been processed or visited. So we set that value to true. Then we're ready to go with the initialization to dive into the processing of our queue. We start our while loop, and the condition to stop is once the front of the queue reaches the back of the queue. So we're going to be adding more nodes onto the queue, but we're also going to be processing one at a time. Potentially, for each iteration of this while loop, we could be adding multiple nodes to the end of the queue, but we're only processing one node at the front of the queue at a time per iteration. So the end of the queue will grow potentially faster than we can process the front of the queue. But when we're done the algorithm, we will have processed all of the nodes if the graph is completely connected. And so we should expect at some point that we will have processed all of those nodes and no more nodes will be placed at the end of the queue. And so the index for front will equal the index for back, and we're done. Okay, we would like to look at and process the very front of the queue first. So we're selecting the next in line. And then we're going to deal with the breadth first search for this particular node at the front of the queue. So to start with, to keep it with the most basic example in your mind, what's going on, we're just selecting what's at the very front, which was the first node that we added to the queue. And so we can just imagine, if we go back to the picture, where do I have my pen? Here we go. Then I'm really processing the root that was passed in as parameter. And if I look at my call to my client code, I'm calling breadth first search with node 0 on my input graph G. So we're starting with node 0 because that's what we asked for in the client code. And so this would be like the first iteration of my loop. Okay. I want a variable to help me keep track of which neighbors. So what are the other nodes that are in the adjacency list for the current node I'm looking at? So for node 0, I would want to look at its neighbors. If I look at neighbors 1 and 2, so that's for the input graph G, I would be processing node 1 first. So we're going to grab the iterator here that we've got set up from our linked lists. There's quite a lot going on there, so I might break down the syntax here so that you can understand, because I know they wouldn't have done something like this in Comp 155. But you would have to start thinking through these kind of issues if you're going to go off and start programming larger projects and have more complex data structures. So we've got a nested class inside of linked list. How do I get access to that? I could do linked list dot linked list iterator. That's the type for this variable. If I want an iterator, I can store it in that variable. And then the function get I have to just set up, give me an iterator so that I don't, if I want to use this more, and if I was going to write more code inside my graph data structure, I'd probably be grabbing an iterator fairly often. So I've got the method get, and then that gets our linked list, so that way we can grab a list iterator. So I might even simplify this, where I'm getting an iterator. I might go write a one-line method so that I don't have to be writing that everywhere else in my graph data structure. And we kind of already did something like this with get itself. What does it look like? Well, it's just simplifying the operation to grab one of these linked lists. Okay. Once we've got an iterator, then I've got my for loop. I don't have to initialize my iterator, which is already done in this line. Really, we could have everything on line 61. We could place it right where you would normally see the initialization. Say, for example, int I equals 0. It's the same deal at the beginning of your for loop. You could place this line and have it function still. It's just that it's quite a lot to look at. So I leave it out and I separate it on its own line. And then with my iterator, for each iteration, the stop condition would be, okay, do I have another node to process in the linked list? So I'm calling hasNext from my list methods. If that's true, then I'll continue on and then I will process that next node in the adjacency list. And then I could put v.next. Let's see, and I would compile and run my code. If I place that, and we have v.next, it will update my iterator. And so it makes sense, instead of doing I++, our iterator would advance to the next node in the linked list. Okay, that should function the same now. It's a bit cleaner within the syntax of a for loop instead of placing it on its own at the end. And then we start to process the list. We are grabbing the current node for the current position for the iterator. Once we get the value for that, so this will be equal to 1. If we grab the first node out of linked list for 0, and so w is equal to 1. If it has not been visited yet, so the visited array would contain the value false. And since we use the not operation, then we would process this node. We would place it. We would say, okay, now we have visited it. We would place it at the end of the queue. And then I would know what its parent should be for this node. So for node 1, its parent would be what we're currently considering for this whole iteration. We're considering the linked list for 0. Then we set 0 as the parent for 1. And that's what we've got over in our parents array when we look down, and I'll use the opposite color here. We've got 0 as the parent for 1. And you can see as we build up our tree that we're keeping track with our parents array. What should our tree look like as we do our breadth first search? Okay, that would be the first iteration for the for loop. The next iteration would advance to the next node, and so we would be looking at node 2 next. Whoops. Okay, I'm gonna have to pause and fix that because I was using a shortcut for the other application. Okay, so I hit some kind of random shortcut, did something else in Krita. But we're looking at node 2 to process inside the for loop. What I would like to do is get rid of the red circle. There we go. And then we're doing another iteration where w is equal to the value 2. It's not been visited yet, so then we would mark it as visited, place 2 at the end of the queue, and then set the parent for 2 to also be 0. So going back to our picture then, we're building up our tree. We've got in the parents array, the parent for 2 is 0. And then we've finished processing the linked list for 0. So we're finished with this for loop, and we would move on. The value for front was 0. But after we processed node 0, front gets updated to the value 1. And so then we would be looking at the next node in the queue, and we had placed the node 1 into the queue before we placed the node 2. And so we would go through all of this again for node 1 and look at the linked list for node 1. Going through, and this is the last iteration that I'll do here. We would get the linked list for node 1, and then we'd enter our for loop. The first node in the linked list for 1 would be 0, and we would check our visited array. We know we had already visited it because that had been set at the start. And we would take a look, we'd say, okay, visited. We wouldn't do any of these steps inside our if block, and so it would be completely skipped. So we're not going to do anything because we've already taken care of node 0. It's already part of the tree. And then we would go through and check the next node in the linked list for 1. We'd look at 2. And again, when we look at the value 2, we know it's already been visited, and we had already added it to the tree, and we had already found the parent for 2 as well. It's already been visited. So again, we would not process it. So there isn't anything done once we're processing node 1 at this point. And when that happens in breadth first search, you can see that the node 1, it's a leaf for your tree. So there's no more new nodes added onto the queue in this case. And we're done with the for loop for node 1. And then again, we would continue on with our processing with our while loop. The value back would be equal to 3, and the value front would be equal to 2. And then the next node we have in our queue would be node 2. We haven't processed that yet. So we get set up, we look at the linked list for 2, and we would continue on. So linked list for 2, I could be much more brief with it. You can tell right away just by looking at the linked list that you've got node 0 already processed, it's been visited, node 1, it's already been processed, and then the only one that hasn't been visited yet is node 3. So you know, while we're processing node 2, if we look at the neighbor, be node 3, we would add that on to the end of the queue. So node 3 goes on the end. And we would mark it as visited. We would mark its parent as 2. And then we're pretty much done. You go on, you're finished processing the linked list for the adjacencies for node 2. And then you finally get to the end, you've got the value back would be 4, and then front would be 3. So we're at the very end of our array. We would process node 3, and then there's no more nodes to visit, so there's, you know, it's a leaf node for your tree. Nothing else gets added onto the end of the queue, and we're done our breadth first search. What happens last is that we create an instance of our tree by passing in the parents array into the constructor. And we've already gone through the code for the constructor before. We pass in the parents array, we'll go back up, take a look. And we know that as we iterate through the parents array, we're connecting the edges that we see between each node and its parent. So regardless of the order that you do this, in the end, what you will have is your final breadth first search spanning tree. And in this case, it's not a subtree. So you could have graphs that do not include all of the nodes of the original input, and you'd call that a subgraph. But because our tree has all of the nodes of our graph from the input, it's a spanning tree. And so we wouldn't call it a spanning, we wouldn't call it a subtree either. We would call it a spanning tree. Okay, hopefully that helps you understand the code that's going on there. If you haven't had a chance to try programming this, I would say give it a go. But see how you could do it after my explanation. Try to do it without looking at my code. And then when you need a little bit more you get to the point where you get stuck, you're like, oh, what do I do next? I can't quite remember everything we were going to do in this algorithm. You're pretty much in your mind going off the description and as the best that you can understand the concepts to try to sit down and program it rather than trying to memorize everything. Because if you try to memorize line by line all the code, then you miss the opportunity to do a little bit of debugging and then solidify the concepts. And you have to do the best you can, juggling back and forth, doing your code, your debugging, and then going back to look at reference that I've got here for you. So you'll find you'll make good progress. The more that you do this kind of practice, the better you get at knowing what's going to work for you. And I really encourage you to have that kind of practice for yourself, especially when you go off and start working on your own projects. You'll find you can make much faster progress on your future projects the more that you can practice like that. All right, good luck everybody. We'll see you in class tomorrow. I'm going to have one more video for visualization. And don't worry, you don't have to program that, but I just want to demonstrate, where are you going to place the coordinate pairs so that then you can get a picture, which is a little bit different from when we had the visualization for only the trees, because there's a little bit more going on with graphs.